then it should be there also the next homework if I didn't do something wrong. And now let us return to division. Now we still have this week and next week. I think my plans for the class were a bit ambitious, and most likely will not manage to cover all the things that I was planning. This is for your delight, right? But let us concentrate on dividers. Now, there are two ways to do division faster. It's similar with the multiplication, but somehow different. In multiplication, we relied on high radix, and we relied on carry-save addition. The same story can be done in here, but there is a small difference, which is essential. Not the fact that the partial product matrix for multiplication is like that, and for division is like that, even though the story is coming from there. It's from the fact that there are dependencies, and the quotient digits can be guessed in a sequential way. And this is creating the problem. Now, let us look further, and let us look now on high radix division. Then if I'm doing high radix, let's say I'm doing radix 4, instead of making a guess for a digit at a time, a bit at a time, now I'm making a guess for a digit at a time. Because I am in radix 4, my digits can be 0, 1, 2, 3. Then before I was just making a guess for 1, and I could subtract something or nothing, depending on how I'm doing. Now I make a guess for 2, and then I will have a subtraction which is wider. Then my basic operation is longer, but I have less cycles. Then I already have half of the cycles, but I should not be that happy. It's not because the operand is wider. Now you see I changed from a 4-bit addition to a 6-bit addition. It's not a big deal. The problem is here on how to guess this value. And I can use the straightforward, the brute force approach, and say try with 3, with 2, with 1, and 0, but this will end up in killing all the advantage. Then we don't do that. We have to find another way. But the principle is very much the same. I'm shifting a number of bits depending on the radix. The higher the radix, the more bits I shift. The higher the radix, the more complicated the guess for the quotient digits. Now, one idea would be to make a guess by inspecting few bits, not all the bits which are involved. Then let's say I'm taking 1 digit of the divisor and 2 digits of the dividend, and I'm trying to make a guess for the digit of the quotient. Now, as you see in this example, I'm not wrong. I'm wrong until I get enough value, and enough value means the entire d and k plus 1 bits from z. Then somehow this is not really functioning. Then if I'm relying on a standard representation, this is not functioning, because if I make, this will simplify the story. If I take 1 from here, 2 from here, the guess will be easier. But it's giving me an error. And in order to correct for this error, I have to have some kind of opportunities. And if I'm doing business in radix 10, as in here, there are no such opportunities. However, if I assume a redundant set, I have an opportunity, and I can say, I can write 59 as 6 minus 1. Then I could make a guess of 6 in my example by just looking at 1 digit in D and 2 digits in Z, which simplifies the guess, and then correct later on because I looked for too much. This will preserve the value. But if I don't have redundancy, I don't have such a possibility. Then this is one thing that I learned, that redundancy can and will help me. Now here you have some examples of high radix division. This is radix 4, integer division, and again the guess for the quotient is based on some kind of visual inspection. Then I see in here that this is now my D, and I look at this guy and I see I can subtract 1. It's okay. I cannot subtract anything. Then I'm trying to do just traditional division, which is restoring. Or actually I do not go to the moment of doing the tentative subtraction. I'm just applying visual inspection. In here now I can subtract 1, and it's fine, and in here I can even subtract 2. It's easy said, and easy when I do it with pen and paper. It's not that simple when the computer hardware has to do that. And if you have even higher radix, things are getting a bit more complicated. How do I know 7 is okay here? 8 is too much, 6 is too little. I have to find a way to derive that. And this is the complication behind playing high radix. Now, as I told you, we make a lot of detours in order to arrive to the solution. And now we make a short pit stop in using carry save errors. Remember this diagram. I'm not sure it was like that in the previous case, but this diagram is telling me the relation between D and the shifted partial reminder, and is making a separation between regions. Remember, if I was larger than something, I could do a subtraction. Within certain bounds, I could do nothing. And if I was smaller than something, I was supposed to do an addition. There is this area where I have an overlap in here. Any of the choices will do. And this is actually what is saving me in doing division. The fact that there is overlap, and in these overlapping regions, I make the choice which is making my life nicer. And I can make this kind of division of the dynamic range for the shifted partial reminder. If I am smaller than minus 0.5, I will choose a minus 1. Add and report minus 1. If I'm between minus 0.5 and 0, I'll choose 0. If I am higher than 0, I'll choose 1 and do a subtraction. This is a legitimate choice for my division. And now, based on that, I will try to make the selection not by inspecting all bits of the partial reminder, just some of them. Then, previously what we are doing, we were doing the addition or the subtraction, and we are propagating the carry. And after the carry propagation, which is a complete cycle, I had the next partial reminder and I knew what's going on with that. Now my decision will be done on a partial reminder which is not stored as a number, but as two numbers. We already know that this is faster. It will take me one full header to generate this compression. Now, the question is how to make the difference. Okay, this will not function in all the cases, but I can assume that my number are fractional numbers. And I will, you know, when I'm doing the iteration with addition or whatever, these are the representation of the partial reminder. And I keep them as two numbers, and I call them U and V. it would have been probably more suggestive to be called S and C, because this is sum and this is carry, but doesn't matter, just a convention. Now I'm inspecting from those bits only, 2 bits which are in the integer part and 2 bits in the fractional part. The rest of the bits here I'm just dropping. And what I'm doing will be the following. I will do now an addition of those 2 numbers, which are now truncated. And based on the result of this addition, I'll make my choice. Then instead of computing the partial remainder precisely, I will compute an approximation of it. Then instead of propagating the carry over n bits, I will now take 4 bits from one plus 4 bits on the other, maybe even make a table, like a lookup table, and obtain the result. Now, the advantage of that is that now my iteration is a lot faster, because I do not have to propagate the carry. The disadvantage of that is that I have to be sure that when I'm making a choice, my choice is correct. And in order to know if I'm correct or not, I have to do a kind of error calculation or error estimation. Because I'm dropping all the bits which are beyond this position, this is 2 at power minus 1, 2 at power minus 2, and all those bits here cannot be higher than 1 over 4. Actually, they are 1 over 4 minus unit in last position. Then in here, I can drop 1 over 4, less than. In here, 1 over 4 less than, which means that the estimation of this number will be with no more than 0.5 lower than the reality. Then if I'm making an estimation and I'm saying I am here in this point, I may be in this interval, but no further. So far so good, or not. Then I'm dropping bits in order not to propagate all the carry. 0.25 here, 0.25 here. Then the result, which is here, which is the partial remainder, will be no more than 0.5 far away from the actual partial remainder. The error can be 0, or if all of those are 0, then I have a precise approximation. If there are 1, depending on where I am, I might be somewhere in this region. Now, based on this, which I can do it like a 4-bit addition, or I can implement it with a table, now I will change my decision, and I will make it simple. Then if I am smaller than minus 0.5 with this approximation, I will choose a minus 1. If I am larger than 0, I will choose a 1, otherwise I'll choose a 0. Now, in general, if I would not have had these overlap regions, the fact that I had an error would have created some problems. But now, let us say I'm smaller than minus 0.5, which means I can be between minus 0.5 in the worst case, close to, and that value plus 0.5. Then I will never have a higher value than 0. And when I don't have a higher value than 0, I can always choose a minus 1 and do an addition. The same story when I am in higher than, when I'm making a choice for 0. I make a choice for 0 where I'm in this region, but I could be also in this part. Then if I am here, I can be maybe also here. But in here, the choice for 0 is still legitimate. Now, if my diagram will require, more precision, then I cannot check things in the way I just did. I will have to extend the number of bits that I'm inspecting here. Are you with me? You have very happy faces. Then, in normal division, what we do is we compute the partial remainder, and based on the partial remainder, we make the choice with such a diagram. The diagram depends on the way I'm doing the division. This is radix 2 division, then shift. Because in this diagram there is some overlap, because in the neutral zone, I can do things or I can leave it the way it is, this gives me some freedom. Now, I'm speculating on this freedom, and instead of propagating the carry and precisely computing the partial remainder, I will just compute an approximation of it, which is no more far away than 0.5 from the reality. Because of these overlapping regions, this approximation can help me to make a choice which is still good. Then that complication I did not have for multiplication, because for multiplication I had no driving value in choices. I was just accumulating stuff. In here, I have to drive my choice. And in order to do that, I have to make an approximation of the partial remainder. Now, the cycle time is the time which will take for this approximation to be computed, which can be, I don't know, a 4-bit addition or a lookup table, plus the logic which is doing the selection. Then in each cycle, I want a lot, because I managed to make the cycle faster. And this is the structure of my divider now. It's very much similar. That I am doing normal division, normal iterations. Now I'm keeping the partial remainder in 2 registers. I'm inspecting from these registers 4 bits each iteration. Based on this inspection, you know, I can report them as they are, and here I have a lookup table, or I do the addition and then I implement something. Doesn't matter how I do it here, I'll have some delay. And based on this, I will determine the digit in the quotient. And this will tell me what to do. You know, do something, do nothing, add, subtract, whatever. And then I have now these 2 numbers plus the new one, which will be now reduced to 2, and this is my new partial remainder. Then my iteration is determined by this kind of critical path. In the last iteration, when I'm done and everything is fine, I would have to compute the remainder by propagating the carry here. Now, I could use this technique also in SRT, but there is a small problem. If I do SRT, when D is getting close to 1, this boundary is getting close to 0, and then I do not have enough room to allow for errors. And this is not functioning in this algorithm. Now, is this story clear? Yes, no, maybe, we don't know. We have no clue. Are there any questions? Now, I will tell you the same story, but in a different way. This is the diagram that we were discussing before, which relates D with the shifted partial remainder and allows me to make decision on which kind of digit to choose. And this is the same, but in a nicer way. Those two are telling me the same story. Now, what I have, this is D, which is between 0.5 and 1. And this is the dynamic range for the shifted partial remainder. the shifted partial reminder, you know, because I start with a value which is within this dynamic range, the shifted partial reminder cannot be smaller than or larger initially after this one when this is, you know, close to 1.5, that cannot go beyond these limits. Then values in this area are not feasible. Then you see I look in positive and negative parts. And those are the separation lines, which are actually these lines. But it's a different way of looking at the diagram, which has the advantage that will help us to design better divider. The story in this case is the same. Now, what do I see here? I see that whenever after the shift I am in this area, I do not have to do anything. You know, here I'm, you know, within the boundaries of the dynamic range of D in this area. Now, if I am in this area, which is exactly this one, if I am in this area, including from 0, I can choose a 1 and do a subtraction. If I am in this area under 0, I can choose a -1 and do an addition. You see there is an overlap between this. Then from here to here it's -1, from here to here it's 1, from here to here it's a 0. Now my job is to try to partition this region in such a way that by inspecting bits of D and bits of P, which is the divisor and the shifted partial reminder, to make the choice for the next quotient. And I have to make choices which are okay, which will make me converge to the result. Now, the easiest way to make the choice is to try only to inspect the value of the shifted partial reminder. If I can do that, I can partition this area, which is the feasible area, in parts where my choices are clear. And this is exactly this line. Then if my partial reminder is smaller or equal to -0.5, I'll choose a -1. If it's larger than 0, I'll choose a 1. If it's in between, I choose a 0. Now, this is the division working for radix 2 and assuming some kind of limitations for D. I have a certain dynamic range for it. If I'm changing the dynamic range, this diagram is changing. If I'm changing the radix, this diagram is also changing. But what is important is that if I make such a diagram for a certain division, then I decide what the division algorithm is, and I decide what the dynamic range of D is, I can get such a plot, which I can do with a computer program, and then my job in designing the divider will boil down to some kind of geometrical separation. I just have to draw some lines in such a way that my separation is nice. And this is making now an opening towards going higher radix. Then once again, the small diagram in the top and this diagram are telling me the same story. There are two faces of the same person, but this one is more suggestive. Okay. Now this is a revisit on how you do calculation for the when you, I don't know why this slide is here, it should have been earlier, but anyway, good that it's here. Now this is about that inspection that we have for using carry-save headers. You see, I'm doing an addition, and then based on the result and some combinational logic, I decide if it's 0 or not, which is the sign. I would expect that in practice I will not implement it like that. I will just make a lookup table, which would be most likely faster. Okay. Now, let us make our first step towards a really fast division. This is radix 4. Now, what is happening in radix 4, as I said, I shift with 2 positions, and now I have to subtract something. Because I shift with 2 positions, my dynamic range, I still start with a value which is between d and minus d. But my dynamic range now will extend, and my maximum positive value will be 4d, and the smallest value will be minus 4d. Now, depending on where I am in here, I may have to apply different kind of corrective subtractions in order to converge to the results. If I am, let's say, in this area, I can subtract 3d. Because a subtraction with 3d will bring me into the normalized value. In here, a subtraction with 2d will be good. In here, 1d will be good. In here, I can leave it as it is. In here, I need to do an addition with d. In here, I have to add 2d. And in here, I have to add 3d. Remember, always my goal is to make a selection for the quotient digit in such a way that I'm normalizing the shifted partial product. If I'm not doing that, my division will not give you right results. And then my job will be to split this dynamic range in parts, then to look at the shifted partial product, and based on what I see, to determine the digit and do whatever I have to do. Again, I have these overlaps. In this part in here, I always have to subtract 3d. There is no other option. But in this part in here, I may go for 2 or 3. In here, I may go for 1 or 2, 0 or 1, minus 1, 0, and so forth and so on. Now, the question is how to make that choice in a simple way. Okay? We all know the complicated way. And the complicated way, we'll start to compare. Let's say, first of all, I would look if I'm positive or negative. That's easy, it's trivial. Now, depending on where I am, I will start trying to investigate where to go. And I can be, optimistic and start from here, or I can start from here, but eventually I may have to do 3 comparisons before I know what the quotient is, and this is forget it. The cycle will explode, and the fact that I'm doing radix 4 will be useless. That's not the thing we'll do. What we'll do is we'll draw this diagram, but now it's for radix 4. Remember the lines? This. Okay? Now I have them in this way. Then I'm still 0.5 to almost 1. And then when I'm shifting, I have these separation lines. And now in this one, from here till here, I have a good choice for 3, a good choice for 2, a good choice for 1, a good choice for 0. And I also have the overlap. Now I will try to make separations by inspecting bits of the shifted partial remainder, and depending on those bits, to say where I am. Let's say if I am under this line, which is under 0.5, I'll choose a 0. If I am under 1, but bigger than 0.5, I choose a 1. If I am higher than 2, I can choose a 3. Now, if I am in this area, I have a problem. Because I have to embed a separation line, which will allow me by a comparison to determine the quotient. But somehow I cannot make if I try to put it here, then this will make that kind of cut. And my cut will be, under it will be 2, on the top of it will be 3. But in this area in here, on this triangle, the choice of a 3 is wrong. Because in here I cannot choose a 3. It's not a legitimate choice. If I put the cut in here, then I will have another problem now with making a choice of 2 whenever 2 is not okay. Then what I see is that one line will not be enough. Then I put a staircase. And then I say, if D is smaller than this, and P is smaller than this, I choose a 2. If D is smaller than this and P is larger than that, I choose a 3. Whenever D is larger than this, I make the comparison on P on this one. Then you already see that while for radix 2 I was just looking at the partial product, now I'm also inspecting bits of D. Now that's one part. The second part is that this is the precise diagram. If I am combining this diagram with the fact that I am computing the partial remainder not precisely, but as an estimate, I will always have, based on that estimate, a value which is not the real value, but which is an area. Let's say if my estimate is here, I can be anywhere in this region, because I drop some kind of parts of it, and I can be anywhere in this area. If my estimate is here, I can be anywhere in that area. Then I have essentially two things to do. I have to determine that kind of separation lines, and I also have to be sure that that uncertainty region is not too big. Because if the uncertainty region is too big, my choice might be wrong. Let's assume that I am in this area, okay, and the uncertainty region is larger. Then I will choose a 2, but I could also be in this area based on the 2. Then assume that this uncertainty region is the 2 of them. Okay? And I am here, and I could be everywhere in this. Based on the fact that I'm here, and on this design, I will choose a 2. However, I could have been also here in this area. And in that area, a choice of 2 is not correct. Then, first is geometry, I have to draw lines. And second is I have to think about the number of bits that I have to inspect in order not to have wrong choices. Now, if I understood that, I can make any divider I like and please. Because the PD plot, this is called the PD plot, I obtain with a program in MATLAB or whatever. Then I assume dynamic ranges. I make the PD plot depending on the radix. I can make higher radix. I will have more lines like that. I will embed some separation lines and some staircase, whatever, and then this will give me the quotient selection. The rest is trivial. The rest is just, that iteration. Get the two numbers which are my previous partial product, make the choice for Q, and generate what you have to add or subtract from it, and then you are in business. Then my life was saved by the fact that I have this overlap. That in some cases I can make choices which are not unique. If I would have had not such a freedom, this design would not have been possible. Okay, now, this is assuming radix 4, SRT with digit set in -3, 3. Now, I can also try to do something else to avoid the 3a factor. Remember, we didn't like it in multiplication also. A to A, 0 are nice. But the 3A factor I have to pre-compute or to rely on some kind of carry save tree to generate it. Now, you see, I can apply this technique with a smaller digit set. There is redundancy in it anyway. And then I can say, I will do the division, it's still radix 4, but the digit set can be -2 to 2. I still have enough redundancy. But I will rely now on digits which are in this set. Now, in order to be able to do that, I have to shrink the dynamic range of my shifted partial product in such a way that it will never get in this area where only the choice of 3 is legitimate, or in this area where only the choice of -3 is legitimate. Then what I will do is I will make a kind of pre-processing. Then I will do something like, you know, a scaling of the numbers. And then based on this scaling, instead of this dynamic range, I will have this one. Okay? Then I will be always between 2/3D and -2/3D, and then after shift, I will never go on higher than this boundary. Then it costed me just the scaling, and I got rid of the 3A. Brilliant, right? What do you think? Will there be a cost? In engineering, this is rule number 1. Whenever you hit in a part, it will pop up somewhere else, right? And it will. And this is where it does. Now you see, this is the new PD plot for the new condition. Now my numbers are scaled. And then after shifting, you know, this is 2 times d/3, no, d/3, 2 times d/3, 4 times, 5 times, 8 times. Then this is now the PD plot for the scaled partial remainder. What do I see? I see that the separation lines are closer to each other. Then I have a larger area where I cannot get numbers. This is not feasible. But now my separation lines are kind of, you know, getting close to each other. And I will have to separate them. And I will not be able to get now straight lines. I will have to make, you know, more complicated step cases. And you see, this means that I would have to inspect more bits from D in order to be able to make that kind of decisions. Then what I got was, I got rid of the 3A or the 3D factor. Then I just have A or D or 2D, then normal or shifted, plus or minus. But this table or this truncated addition will require, you know, more precision. Again, if I am here, I may be in this area. Then if you look at this diagram, and you look at this diagram, this looks nicer. It's simpler. I have 2 lines which are horizontal, and that one is just a simple staircase which has a fracture in here. On the other one, the staircase is more complicated, which means I will have to inspect more bits of D in order to make the choice. Then again, based on this diagram, which actually for signed numbers should be all over the quadrants, because during the process of doing calculations, things may go on this part and on this part, but also D can be negative, which means it will be here. Then if I want to make a real design, I will have to draw it for 4 quadrants. And then determine the separation lines, see how many bits of P and how many bits of D I need to inspect, and then create the content of a lookup table where I should get the digits from. Then I address the lookup table with the with the right or the proper bits of P and D, and then I get the choice. If I make here a mistake, my divider will not function. And that's it. And this is the structure of the divider. I'm keeping the partial product, sum and carry. Depending on the radix, I make shifts, with more or less bits. I inspect in here a number of bits from carry and sum and from the divisor now, which we didn't have before. In this logic, which is most likely a lookup table, I will process those bits from here and those bits from here and make the choice for Q. Now, this together with D, and maybe some more complicated logic in here, because if I have to generate A to A3, D to D3D, I have to rely on some kind of pre-computing or maybe on a carry save header tree, which most likely is the case. Then to generate this, I will put here a number of inputs, and then I make the reduction to 2, and I'm ready for the new iteration. In the final iteration, I do this carry propagation, and I'm done. And this is division. That's how division can be done in high radix. Okay? Now, this is on how to do things with multiplexers or with, because instead of relying on that, on carry save header trees, you can also use multiplexers. Okay, then, practically speaking, in high radix, this is what you have. First of all, you cannot design a divider for any kind of dynamic range, like we did it for addition and multiplication. We said it's 16-bit header or 16-bit multiplier, and there were no restrictions. In here, you have to bring your values within a certain range. And now, depending on that, you may have to apply an extra correction in order to shrink a bit the dynamic range to get rid some of the digits in the redundant set in the quotient. Now, if you do that, you may remove some of the choices and simplify that, but as I told you, your lines in the space will get closer, which means your logic will be more complex. Then if you go for a random kind of radix design, you will get such a diagram. You may apply scaling or not. This for radix 4 scaling, you multiply with 2 over 3, and then you have to make the choice. Now, which direction you should go will depend on what you get from this picture. Where the critical path will be. If you make the radix too large, this will get more complex, and then each iteration will take longer, but you'll have less iterations. If you make the radix too low, then you'll have more iterations, and each iteration will be shorter. Then, for sure, there is a sweet point where it makes sense to place yourself. If you play with the digit set and you try to get rid of some values of the digit set, you have a lot of redundancy, and you can do that. This will increase the number of bits that you will consider from those two. And those are design choices. Now, when you think about the design, the decision on how to design things, what you have to do is you have D in standard, and then you have P in carry save format. then your first idea will be, because P is in carry safe format, I should try not to inspect a lot of bits from P. Because inspecting P means actually inspecting too much the number of bits that you are inspecting in normal format. Then like in here, I have P in carry safe, then this is the value of P that I'm computing, but I have to inspect twice the number of bits. Now, my first idea would be, let's try not to inspect too many of those. Now, if I'm doing that, the uncertainty region is getting narrower but taller, which actually precludes the operation of my divider. Because like in this example, if I am here, the uncertainty region is covering this region, and this region. There is no choice for this which will satisfy all of them. Let's say if I choose this one, and I'm in here, it's fine. But if I'm in here, there is no overlap. Then that kind of tall and narrow uncertainty blocks are not good. If I increase now the number of bits that I'm inspecting in P, I have wider blocks, but which are not that tall, which will allow me always to make a legitimate decision. Actually, my first job is to determine the number of bits that I'm inspecting, then in such a way that I always can embed that kind of uncertainty regions in the diagram without infringing the rules. Okay, we'll discuss about that on Wednesday when we should finish the division and try to get a bit into floating point. Then I publish the solutions on Blackboard, and I think homework 4 is also there, just if you want to try, which I'm sure you will